Hi, my name is Andreas Stockholm.
And I am Andrzej Kucik.
We're working on preventing the next Titanic and are here to present our second entry into our series AI4SeaIce titled Comparing Loss Representations for SAR Sea Ice Concentration Charting. To sail quickly and most importantly safely from point A to point B in the Arctic, ships utilize a so-called sea ice chart, which is a map of the local sea ice conditions. The maps are produced from satellite radar images and are advantageous because of the high image resolution and because it can see through clouds while measuring independently of sunlight, which is particularly useful during the dark Arctic winter. However, radar images are difficult to interpret by untrained eyes, and ambiguities between open water and sea ice are common. To help ensure safety in the cold and remote Arctic, professional sea ice analysts are still to this day producing sea ice charts manually. Sea ice is in constant motion, and therefore ice charts are drawn manually, daily. This is a resource and time consuming endeavor, which we are trying to automate using a unit type model. This has the potential to free human resources and assist in enabling the northern trade routes connecting the Atlantic and Pacific Oceans through the Arctic.
Given the segmentation model, we study its performance under different objective function representations. This can be represented as either regression or classification problems. Regression, because the sea ice concentration is provided as percentage values, and classification, because these values are discretized as 10% bins. We investigate the former with two loss functions, binary cross entropy and mean squared error. For the latter, we use either categorical cross entropy or the earth mover distance squared to incorporate the correlation between the classes into the model's objective. Since the individual classes are not equally distributed, in fact, the classing balance is extremely skewed towards 100% water or sea ice, we also optionally incorporate a loss weighting scheme, where the weights are inversely proportional to the class frequency and normalized to sum up to 1. Note that the scenes contain a variable number of invalid pixels corresponding to landmass, which are discarded during the model's testing and optimization, with each example having the loss function adjusted to be proportional to the number of valid pixels. We measured the model's performance in terms of accuracy and R2 score to better understand how far the predicted values are from the ground truth. We repeated all the experiments fivefold and chose the best performing models in terms of the R2 score in each loss function category for our analysis. The regression-based loss function outperforms the classification ones in terms of the R2 score, with the MSE giving the best result, while the opposite is true for the accuracy. Here, the categorical cross entropy is the best. This remains true regardless of the weighting scheme. However, including the weights in the loss function helps in the average per class accuracy because it improves the performance of the underrepresented intermediate classes.
Inspecting our results on the test scene on the left, we see that the models trained with the unweighted regression objective have a strong correlation with the ground truth, but contain large variations in the sea ice concentration. Although the unweighted classification objective models achieve lower R2 scores and tend to overpredict 100% sea ice, the visual resemblance to the ground truth is superior. For the weighted regression models, we see lower performance, noise in the near range SAR region located in the right side of the image, and much more blurry predictions. The weighted classification models also suffer from less detailed predictions but are resistant to the noise in the near range SAR field.
To summarize, generally we see a strong resemblance between our model's predictions and the human labeled ice charts. Regression optimized models achieve the best quantitative results with respect to our primary metric, the R2 score, but suffer from large variations in sea ice concentration and are less robust to SAR noise. Classification-based models output the best accuracy values and the sharpest and most detailed charts. However, they overpredict 100% sea ice. And finally, weighting the loss function helps with the intermediate class predictions, but also produces blurry charts. In the future, we plan to investigate the influence of balancing the dataset, using different sampling techniques or decoupling the classes during the training to improve the model's performance.
You can find our model and loss function code and our previous work here, which also describes our practical approach in more detail. Thank you so much for listening.